let's continue looking at arithmetic in the Islamic world. And when I first started this class, I started making comments about like the Hindu Arabic number system, how slick and cool and good it was. And it's so slick that you really don't notice its power. And I think the main way the power comes from is it's kind of like it's from its positional structure. So we'll see other number systems like, which would be over-cipherized. So they'd have symbols for 1 through 9, and then 10 through 90, and then 100 through 900. Ones where the position doesn't matter, like it's kind of like a tally system. We'll see that with the Egyptians. The nice thing about the positional system is, well, there's a couple of nice things. Firstly, it really kind of structures the algorithms. So for example, when you're doing addition or subtraction, you've got to line up the positions, right? You've got to line up the units, you've got to line up the 10s, the 20s, etc. They've got to line up one below the other. The interesting thing comes for when we're doing division and multiplication, because it's a positional system, when you're operating on one digit on another digit, it's kind of like the power of 10 or the power of 60 that's involved that's important. And that determines what position the answer goes. So for example, if we have like A, B, C like this, and we do E, F, and so we've lined it up so that A is 100, sorry, B is 10, C is units. Like when the A interacts with the F, so we like say we do A times F, we've got 100 times a unit, so the answer is going to be 100. So somewhere else we're going to be doing the answer. So up here, what letters, G, H, I, J, K, whatever, A times F goes in the hundreds, it's contributing to this position right there. Now, that's good because knowing this, we can do multiplication efficiently. But it's actually bigger than that because it gives this idea then of, multiplying one by another, it's got a position, and that determines the position of the answer. That's going to lead directly into when we do polynomials, right? Because it's going to be the same thing, the same system, if instead of the number A, B, C, we had the polynomial A times x squared plus B times x plus C times EX plus F. There, when we've got a constant times a square, the answer is going to be a square. Now, this is all really kind of obvious, but it wasn't until the positional number system came along that people realized, hey, this is how we should be doing polynomials. So this kind of way of doing that, this algorithmic way of doing mathematics, kind of helped organize mathematics and helped then also to let mathematics sort of go on a future path, like one that we recognize, like with algebra. And so algebra is, one of the things that we recognize the medieval Islamic world for sort of contributing to. Now, not everything was so clear right from the start, right? So we've seen that they had these numbers around the year 800, and we see, like with their use of fractions, they have this weird way of doing fractions where they use the fractions in base 60, and it's just because, you know, people grew up, they were taught base 60 fractions, and that's the thing that everyone did, and there was really no need for them to do decimal fractions, even though they discovered it again and again. And why did they discover it? Because of the positional system, right? So you've got a decimal fraction 0.123, right? 1 is a tenth, the 2 is 200th, whatever. And so all the algorithms that they had for integers applies to decimal fractions as well. And so there's really, they had no need to introduce the complication of base 60 fractions, because decimal fractions did the job perfectly well. So we kind of see things here like how ideas kind of advance math, and that unless there's great need to change something, there's a lot of inertia, and so the way that people did things tends to stay the same, even though they know they should know better. So one of the things I talked about last week was the idea of finding square roots. Has anyone tried doing that square root yet? Had anyone ever seen that before? It's kind of weird to think that, you know, well, it's true that taking a square root is an arithmetic operation. And taking square roots is important, right? Because we know from solving quadratic formulas, we know from the Pythagorean theorem, we know that square roots are sort of like a basic operation that you need to be able to do, more so than the other roots. Okay, now, so let me give you an example of how they could have used decimal fractions by doing like a square root. So let's look at the square root of 3. Okay, and so we can sort of set up the operation. 3, and we have the decimal point here. And I'm going to go into decimal fractions, so we do it in pairs, right? Because we're taking a square root. Square roots halve the number of digits. Okay, and so what am I going to do? So the first thing I'm going to do is I'm going to look at the 3. I'm going to take the square root of 3. The biggest square that's smaller than 3 is 1. So I'm going, hang on. And I do it, I'm going to have 3, 0, 0, and I've got to have a line on top. And I'm going to put a 1 there, because that's a square root of 3. And then I'm going to take away that 1 from here, and so below the 3, I'm going to have 2. And then I take the 1 downstairs, I double it, and I move it then one place to the right, and so I put it in this column here. So maybe I'll put a line here to show I'm doing it. Put it there, so that becomes like a 20 in that column there. Okay, and now I've got to find the number x. So what is going to be this digit here, which is going to be, it's 1 point something, because that's where I'm putting my decimal place. Well, I want 20 plus x times x to be less than 200. I always get nervous with this because I always feel like I'm going to do something wrong. What number is going to go there? What's the biggest x for that's true? Oh, know what the square root of 3 is, right? It's 1.7. So the answer must be 7. Is that true? What's 27 times 7? Oops. 27 times 7, 189. Yes, it is true. So we're going to put in 189. So I'm going to put a 7 up here, and then I'm going to subtract 189, and I get 11 as my remainder. And so the square root of 3 is 1.7. And you can see then that I can just keep on going. I take that remainder 11. I have to double the 7, add to it, move it over. So when I double the 7, I get 14. Add it to the 20, I get 34. And then I move the 34 over one column. And then I continue the same thing. I look at, and then I introduce another column over here. And so then I'm going to be looking at 34 plus x times x less than equal to 1100. And I can just keep on going kind of forever. And I'm going to go forever. Why is that? What?
We know what it is.
Well, we know it is. It's square root of 3 is what kind of number?
Irrational.
It's irrational. So this is never going to terminate. Okay. So that's all well and good. Let's have a look at other roots now. How would we do, for example, a cube root? So let's figure out how we would turn that into an algorithm. Okay, so let's do an example. So let's do like the cube root of 9 million, for example. Okay, so when we take a number and we take its cube root, how many digits are we going to have in the answer? How many digits is the cube root of 9 million? So if square root halves the number of digits, what does the cube root do? Divide by 3. Exactly. And so we would put things in units of 3. So we would do 0, 0, 0 is 1 unit, 0, 0, 0, 9. And so we see that the answer is going to be a 3-digit number. Okay. And so we put the line over here. And so we act on the first thing, 9. So what number are we going to put above the 9? Cube root of 2, yeah. Because we know that 2 cubed is 8, and that works. And so we're going to subtract 8 from 9, and we get 1. And now we're going to work on 1,000. Now, what operation do we do? So remember last time we doubled it, and we had the 20 plus x times x. What do we got to do in this case here? Well, it's a cube, so let's do a little sidebar here. So we want 20 plus x cubed. We want that to equal 9,000. Okay, now we already did the 20 cubed. That was the 8,000, and we've subtracted from that. So we've got everything else instead. So we've got, what do we got? So how do we cube something? What algebraic object do we use to help us expand a cube? So remember we had For a square, it's 1, 2, 1. What is it for a cube? 1, 3, 3, 1. What is this? Pascal's triangle, right? Which was invented in, supposedly in 1600, although of course you can find it in Arabic texts in the year Al-Karaji did it in 1000. You can find it in Chinese texts, you can find it in Indian texts, whatever. Whenever you had to expand a polynomial, you need Pascal's triangle. So actually, it's okay to call it Pascal's triangle because what does Pascal triangles give you? It gives you two things. One, it gives you the coefficients when you expand 1 plus x to the n. What's the second thing it gives you? What branch of mathematics? So it's used in algebra and it's used in sort of number theory combinatorics, right? So it's used in expansion of a polynomial and it's used in combinatorics, right? Because this is n choose k, the digits there, okay? And Pascal was actually the first person to realize that those things are actually the same thing. That the coefficients, when you expand 1 plus x to the n, is just the n choose k. So before that, all the Arabic and Chinese and Indian, they were only doing either one field or another. So it's okay to give Pascal some credit for Pascal's triangle. Anyway, so what do we get? So we get So we get 3 times 20 squared times x. Okay. Make sure my times and my x's don't get up. Plus 3 times 20 x squared plus x cubed equals 1,000. Just got that in. Okay, and so how would so that's not the most computationally efficient way to write that. We should write that as, say, 20 squared is it's like 1,200 plus x how we should write this. No, sorry, I got it wrong. It's going to be the 60. 60 plus x times x plus 1,200 times x. Did I do the right thing there? If I expand that out, I get the same thing as I did upstairs, right? Is this the same as this?
Is that x squared or 20?
It's 3 times 20 squared times x, so that's 1,200x. And if I multiply that out, I do get 1,200x. I get 60 times x squared, and I believe I do get 60 times x squared plus x cubed. Okay, why is this more efficient computationally? Right, so if I did 1,200 times x, that's one computation. If I do 60 times x squared, that's 2 computations. So I add that, that becomes 3, right? I've got to do x times 60. So that's 2. So 2 plus 1 is 3. To do the x cubed, that's 2 computations. So that's 5 total. Then I've got 2 additions. So that's 7 different pieces of arithmetic to do it this way. Whereas this way, I do 60 plus x, that's 1. Multiply it by x, that's 2. I add 1200, that's 3. I multiply it by x, it's 4. So it's 4 versus 7 computations. So it's much more efficient to do this. And the bigger the polynomial gets, the more savings you're going to get. Okay. So the important things for us, though, is the 60 and the 1200. So whereas before we only had one thing in the bottom, which was just the coefficient of x. Remember, we just doubled it. Here, we've got 2 coefficients. We're going to have 3 times the coefficient and 3 times our number and 3 times our number squared. So down here, we've got to have something for the root and something for the square. So we've got to keep track of the coefficients. Okay, and so we take our 2 and we triple it to get 6, and then we're doing our shifting over, and we take our 6 and we want to have 60 over here. With our, right, so and by our shift, because the reason why it's 20 is, right, because when we're dealing with the second place, this 2 turns into a 20. So that's why we have 3 times 20 there. And for the square, we want 3 times 20 squared, which is 1200. Okay, and so now we want to solve this thing here to be less than 1,000. Okay, and what's that going to be? That's a really easy one, actually. It's the easiest one I've asked so far. What does it have to be? What does x have to be? In this equation here, because remember we want it to be less than 1,000. Less than or equal to 1,000. Right, because of that 1,200 there, this has got to be 0 right here. Okay, and so then we subtract 0 from it, and so now we're dealing with 1,000,000. And now our equation becomes, so now we've gone from 20 to 200. So 3 times 200 is 600, and 200 squared is, I add 2 zeros, don't I? So they're now my coefficients that I have to worry about. So I have to worry about 600 plus x times x plus 120,000 times x being less than or equal to 1,000,000. And it's not really that hard, right? Because the 120,000 dominates the whole thing. And it looks like it could be 8. The answer is either going to be 8 or 7, because 8 times 120,000 is 960,000, whereas 8 times 608. I think it's going to be 8. As long as when I plug in 8 times 608 plus 120,000 times 8, as long as that's less than 1 million, which I think it is. Can someone do that for me?
Yeah.
So what is it?
It's 989,184.
So then I subtract that from 1 million, and I'm going to get my remainder. So what was that? That was around 10,000 and something, was it?
989,184. Oh, like minus?
Subtract that from 1 million.
10,816.
So the answer is 208 with the remainder 10,816, and we can write that then as erase some things. The answer is going to be 208 and 10,816, and then the denominator is going to be 209 cubed minus 208 cubed, which is 3 times 208 squared plus 3 times 208 plus 1, I believe. Okay, and so on. You can do any kind of root that you like, except on the bottom. So if you do an nth root, you're going to have n minus 1 coefficients underneath, which you have to take account of, which is going to come from Pascal's triangle. So for example, in the book, there's this famous example that was done by Al-Kashi in 1429 when he found the 5th root where was it? How did you find the 5th root hang on, that's millions, billions, trillion. 44,240,899,506,197. Okay. Which, of course, since it's a 5th root, you have a 5th of the digits, and so the answer is a 3-digit number. It goes through the text and it shows an example of how he did it. We won't go through the details, but you can kind of see where it's coming from. So the important thing is they know they're using the positional system with the digits, and they're using Pascal's triangle. So they're showing a really sort of intimate knowledge of how numbers work. And this is why this is impressive. Okay.
So for our answer, would it be 208 plus that fraction?
Plus that fraction, right.
Okay.
So what is happening what the arithmetic is doing is, you're saying, what we're doing is what is the kth root of some number? And so what this arithmetic procedure does is it finds the highest kth power, which is just less than it, plus a remainder, and we approximate this then as n plus r over n plus 1 to the k minus n to the k. So the arithmetic is just finding r, and then finding, so you find that n and you find that r, that's what the procedure of that arithmetic does, and then that's the approximation that you use for that nth root. And so I think that's pretty impressive. I find it a little bit amusing, right? Because, as I said, square roots are important. So if you were, a person would need to figure out square roots for various reasons. As I said, because if they're solving quadratic equations or they're doing something with Pythagorean theorem, so this would come up if they were doing certain kinds of problems. Fifth powers, right, would never come up, really. So Al-Kashi doing the fifth root of 44 trillion is really just a piece of mathematics for, it's like art for art's sake kind of thing. He's just doing it because, wow, I understand this so well that I can do this. It's kind of like, you know, those painters who do drapery, can paint clothing really well. They show off by doing it. So this is really Al-Kashi showing off by doing something which at the time no one would ever need, but he showed that he could do it. So I think it's, I think that's pretty impressive. But also I think that is a basic human thing that happens. That people develop something, and this happens in art and science all the time, that people develop something for some useful things, and then they go beyond what is useful, and they develop it for its own sake, and then later on, someone might come around and say, hey, that's actually useful, I can need this for things, you know, like, I think it was Lord Kelvin who said in the 19th century something like, vector spaces, you know, total abstract nonsense, no one will ever need to do anything with a vector space. And of course, vector spaces, you need to do any kind of thing, you know, like navigation or all kinds of useful things. It's like super useful. Okay. So that's 35 minutes. I think I'll stop here.